Thanks. So I'm going to talk about variability of water in the UTLS, and this is work that Hao Yi, my graduate student, has done. He's unfortunately chained to his desk right now finishing his thesis, so I'm forced to present his work. Now, we kind of understand what it is that's driving changes in stratospheric water, and basically as water rises through the cold point, it acts like a cold trap, and it regulates the water, and it's variability in the cold point temperature that drives variability in water vapor. And we know what causes the variability in cold trap temperature, things like QBO, Brewer-Dobson circulation, the strength of that. And I've been arguing in some recent papers that tropospheric temperature also influences stratospheric water vapor through influence on cold point. And then we'll talk about other ways tropospheric temperature might influence stratospheric water vapor. And in fact, in a paper we did a few years ago, this is a time series. The black line is MLS. This is 82 millibars, so just above the tropical tropopause. This is a tropical average. And what you see is that we can fit the water vapor to these terms, and that's what these dashed lines are, using Mira and Era interim regressors for tropospheric temperature, Brewer-Dobson circulation, and QBO. You see, you get a really excellent fit. So if you tell me the QBO phase, the strength of Brewer-Dobson circulation at tropospheric temperature, I can tell you how much water is in the lower stratosphere. So this we published a few years ago. And so what Hao thought is, well, let's look at the spatial distribution of this. This is all tropical average, is what we've done. So what we're going to do is we're going to take the tropics, we're going to break it up into a bunch of boxes. And in each box, we have a time series of MLS water vapor. And then what we're going to do is we're going to do the same regression on the time series in each box. And we're going to use, so this depends on latitude and longitude, but we're going to use tropical average regressors. So the regressors are going to be the same for every box. And then what we're going to do is we're going to calculate these coefficients, how important each of these terms are as a function of latitude and longitude. Okay? And so it's a really very interesting idea, I thought. And when we do this, I'll go over that. If you want to know what the regressors are, I can answer those questions. This is the answer we get. So this is tropospheric temperature. So you see that when the troposphere warms up, you get this big increase in water over the western Pacific. And over the central Pacific, you really don't get much of a change. This is the Brewer-Dobson circulation. So again, Brewer-Dobson circulation, when it strengthens, that tends to cool the tropopause, and essentially it reduces it everywhere. There's some structure, and Hal's looking into sort of understanding why we're getting maybe a bigger response here than here. It may have to do with the relative humidity of the base state. And here's the QBO. So you can see here's a QBO pattern. Most of the QBOs happening sort of in the western and over Africa and Atlantic Ocean. And so this is interesting, but it's a little bit hard to interpret just these plots. What we're going to do is, let's turn to our trajectory model. So, I should say, this is everything I'm going to show you is at 100 millibars. So that's right in the middle of the TTL. So we're going to turn to our trajectory model. So our trajectory model launches millions of trajectories in the TTL, but below the cold point. And so it initializes them, and then it uses reanalysis winds to advect the parcels up into the stratosphere. And then we use the reanalysis temperatures to tell us what's the coldest point the trajectory saw. This is the Lagrangian cold point, and that determines the amount of water vapor on the parcel. So the trajectory model only has temperature in it. Okay, so to the extent that the trajectory model can simulate the MLS data, then it says that temperature is what's driving it. To the extent it can't, it tells you maybe something else is going on. And this model has been very successful. This is a paper from something Mark and I wrote about many years ago at this point. And this is the MLS pattern on December 30th, 2009. This is a trajectory model. And you can see they agree quite well. And I won't belabor that point. The model does a really good job, though. And so what we're going to do is we're going to do the same thing with the trajectory model we did with the MLS data. We've got time series of the trajectory model in each of these boxes. And then we're going to fit each one using exactly the same model. And so we're going to come up with coefficients for the trajectory model that we can compare to the coefficients from MLS. And we can ask the question, how well does the trajectory model do in reproducing the dependence on these terms? And so this is the answer. So on the left side are the coefficients you get from MLS. the right side of the coefficients from the trajectory model. So let's look at the bottom two panels first, Brewer-Dobson and QBO. And you see the trajectory model does an outstanding job of reproducing the response of water vapor to the Brewer-Dobson and QBO. And you kind of expect that because Brewer-Dobson and QBO both influence water through temperature. And temperature is the only thing that's in the trajectory model. And it is in the trajectory model. So you expect that the trajectory model should do a good job. But the trajectory model actually does probably a better job than I would have predicted in advance. I mean, it gets the pattern right almost exactly. So that's heartening that it's getting those things right. And but so now let's look at this. Now this, it doesn't do as good a job. So you see that there's some real obvious differences between the MLS and trajectory model when you're looking at the response to tropospheric temperature. And in particular, you see there's a big difference in the central equatorial Pacific. This is really where the difference is. And so we want to think about this. I mean, is this telling us we're missing a process? What does this tell us that's going on? Okay, so let's look at the trajectory model and see if we can understand why does the trajectory model predict this pattern. Okay, so you've got increases in water here and decreases in water here as the troposphere warms. So what's going on? Well, the warming of the troposphere is associated with ENSO events over this time period. Okay, so in the normal, what I'll call neutral ENSO conditions, you have this is a line along the equator in longitude. So you have Africa here, Western Pacific, South America here. And in ENSO neutral conditions, most of your convection is above the Western Pacific, and that tends to warm the troposphere. But then you have this cold pool that sits above the convection in the Western Pacific. As you switch to El Nino conditions, you warm the troposphere and you shift convection. And as you shift convection, the cold pool gets dragged along with it. Okay? So if we look at a top-down view, the cold pool is normally located over the Western Pacific. But then as you shift to ENSO, the cold pool moves over to the Eastern Pacific, or Central Pacific. And along with that shift, the troposphere is warming because you're going into an El Nino. So the troposphere is warming. That means that if you regress TTL temperatures, 100 millibar temperatures, against tropical average temperatures, this is what the pattern gets. As the tropics warm up, you get a warming of the 100 millibar surface here, and you get a cooling of the 100 millibar surface here. And that just reflects the fact that convection is shifting as the troposphere warms up during an ENSO event. And so now we look at this pattern, we understand why the trajectory model predicts this. Okay? Because as this is the regression coefficient, how much water vapor changes per degree of warming of the troposphere. And as the troposphere warms up, temperatures here increase, hence you get more water vapor, and temperatures here decrease, and hence you get less water vapor. So this makes complete sense once you understand how the temperatures vary with a warming troposphere during an El Nino cycle. So when we compare this to MLS, what we see is that MLS is really the outlier here. MLS is what doesn't make sense. We know temperatures here are decreasing, but the MLS does not show water vapor going down in a way that the trajectory model does. And so you think about, okay, what are the possibilities? Okay, so it could be errors in MLS. It could be errors in the reanalysis. And I tend to discount those. I mean, you can't ever eliminate them. But I discount them just because the model does such a good job for things like the Brewer-Dobson and the QBO and these other terms. And it's really focused on one area of the tropics. It's really hard for me to believe that there's an error in the analysis that's giving you that. So it's probably missing physics. Okay? And so you could say, well, maybe it's missing microphysics. You know, our trajectory model has the simplest microphysics you can imagine, which is just we remove water at 100% relative humidity. Maybe you need to have supersaturation. Maybe you need to have these other things. We've tested some of them. We can add supersaturation to our model. It doesn't fix it. But in general, again, given the location of where it is, I think there's a more likely, and that's ice lofting. So in this region, you're getting ice that's lofted into the stratosphere, where the ice, and that's happening because the troposphere is warming. So you're getting more CAPE, more convection. That lofts more into the TTL where it evaporates. And you can explain this then in terms of two things that are basically canceling each other. Temperatures are lower. That tends to reduce water. But then you're lofting more ice into the stratosphere. And that basically cancels it out. And that's why you get essentially a very weak response here compared to the trajectory model, which has no ice lofting. It just has temperature in it. And so I'll show one last plot before I conclude. This is a plot from a paper Melody Avery wrote that Hal and I are co-authors on that's currently in review. And basically, I think she actually showed a plot of this, but I'll show it again. It's a time series of calypso ice water above the tropopause. And the red line is the central equatorial Pacific. That's the region where where the trajectory model predicts it would decrease, but we don't see it decreasing. And these dashed vertical lines are ENSO events. So you can see whenever there's an ENSO event, which corresponds to the convection shifting over, you see this massive blast of ice into the region. And so Hal is hard at work trying to really nail down this. I think we have a plausible case. My intuition says this is the right explanation. I think we may not be able to quite prove it yet, but I think we're getting close to being able to show that temperature is the primary determinant of water vapor variability, but ice lofting plays a small role. And I think we've looked into the climate models and previously published work, and on longer time scales, ice is very important for understanding the trends. So I'll just conclude by saying that we've used MLS measurements and trajectory models to show that the impact of the QBO and the Brewer-Dobson circulation are really well explained just through their impact on temperature. And our trajectory model does a great job on those. TTL temperatures are not sufficient to explain the impact of tropospheric temperatures on water. And I think that our hypothesis is that tropospheric temperatures are associated with ice lofting, and that you need that to explain the spatial pattern of the response. Thanks.
Joan.
So I wondered if you could give us some interpretation of why your QBO regression coefficient pattern has zonal asymmetry, so much zonal asymmetry.
Yeah, that's a really good question. My guess is that it has to do with the relative humidity pattern. We can't. That's one thing that Hal's working on right now. But if you look at the relative humidity pattern, you get a big response where the relative humidity is high. So my guess is that if the relative humidity is low, then the QBO may not be strong enough to saturate the air in those regions. That's just a guess. But I think there's interesting stuff there.
Yeah, that maybe just throw it out there. You showed ENSO affecting the temperature, and the pattern didn't really quite look the same. One is sort of off the equator, your ENSO calculation, whereas the regression showed it peaking on the equator. Actually, I'm just wondering if the QBO pattern might include some of that interannual variability.
Yeah, I mean, certainly in a 10-year time series, you have to be worried about correlations between the regressors. And we've looked at that. We don't see the regressors, at least in the tropical average, are that well correlated. But I think that's one of the things we need to look at is the regression, the correlation in the grid scale. That's actually a good point.
Yeah, I was writing you got the question. The temperature is tropospheric temperature, right?
Yes, 500 millibar temperatures.
Yeah, but it also that TTL time can also sufficient. So I think that's different between the TTL critical temperature and the tropical temperature, right?
Right. Yeah. Okay. So that's probably awkwardly phrased on my. You're right. What I'm trying to say is that there is some impact of tropospheric temperature on TTL temperature, and that does impact water vapor. But that's not. You need another physical process besides the connection between tropospheric and TTL temperature, and that's ice lofting. That's what I meant to say, but I think you're right. That is awkwardly.
But I think small errors in that connection between the tropospheric and tropopause temperatures can have a big impact, and you have to really evaluate those carefully before you go and attribute the difference to convective lofting, which generally in these detailed models has a small impact. So it's...
I guess I'm not sure what do you mean, small errors in
the temperature fields associated with the temperature response to the ENSO. Small errors in that could cause this.
You mean small errors in the regressors?
Right.
I think those are pretty well. I mean.
Mark? So ice lofting is basically just humidifying the air, bringing up ice, creating saturating the air in the convective region. That's what you mean by
Yeah, ice lofting is a way to get water up there that's decoupled from
Right.
tropopause temperatures.
Well, convection's going to do that. It's going to
Yeah.
bring up ice and it's going to evaporate. Now, most ice falls out, but you just leave humidified air up.
Right.